All right, let's talk about topological entropy damping. It sounds complex, I know, but it's basically a whole new rulebook for how we can control quantum computers. So here's a big question in quantum computing. Can you actually make a quantum computer more powerful just with software? Without having to build brand new, expensive hardware. Can a smart piece of code just tame the chaos inside a quantum processor? Well, it turns out the answer is a huge yes. And we're not just guessing here. This is based on more than 94,000 experiments on some of the world's most advanced quantum computers. The discovery is called the Y sequence, and it's a completely new way to control these machines using just software.
So, how does this all work? Well, this isn't just some clever coding trick. We're actually tapping into the geometry of the quantum world to tame errors.
The secret sauce here is something called the Berry phase. It's a geometric effect. The best way to think about it is with a Foucault pendulum. Imagine one swinging at the North Pole. As the Earth turns underneath it, the pendulum's swing path seems to rotate, right? But there's no force pushing it sideways, it's just following the curve of the Earth. The Y sequence does something really similar, but to a qubit. It changes the qubit's state based on the shape of the operations we perform on it, not by pushing it directly. And that shape is what can protect it from noise. Okay, but here's where things get really cool. This geometric trick isn't a one-size-fits-all kind of deal. It turns out that how you physically lay out the qubits, their shape or topology, dramatically changes what happens. You get 3 totally different modes of control. And you can see those outcomes right here. Depending on that geometric arrangement, the Y sequence can do some pretty amazing things. We're going to look at 3 distinct, predictable results that come out of this. Let's start with Mode 1, Balanced Protection. This is the one you'd likely use for running actual quantum algorithms. So, what happens when you arrange the qubits in a simple line? The Y sequence gives you this balanced error suppression, and the results are, well, they're pretty impressive. We're talking a 7.35% improvement for 2-qubit states and a solid 12.1% for 3-qubit states. And remember, this is a real, measured boost in performance with 0 changes to the hardware. That's a huge win.
All right, so what if we change that geometry? This takes us to the second mode, which is called hyperdamping. And yeah, it's pretty extreme. Now, if you arrange the qubits in a closed loop like a ring, something totally different happens. The system basically locks itself into its lowest energy state. It just aggressively kicks out all its extra energy. In fact, we see 2.3 times more ground states than excited states. Now, you wouldn't use this for running an algorithm, but it's perfect for something like quantum memory, or just hitting a reset button to get all your qubits back to 0 fast. Okay, now we get to what might be the most incredible part of this entire discovery. We're about to see something that seems to flip a fundamental rule of quantum physics on its head, a quantum state that actually flows uphill.
So, for something like 70 years, we've had this bedrock principle in quantum mechanics called T1 relaxation. It's simple. An excited qubit, what we call the 1 state, will always decay back to its stable ground state, the 0 state. Think of a ball rolling down a hill. It's just the natural way of things. Energy goes from high to low. This means you should always find more systems in the ground state than the excited state. Always.
But look at this. Just look at the raw data. This is from a 7-qubit experiment. That orange bar on the right, that's the number of excited states. And it is clearly undeniably higher than the gray bar, which is the ground states. The ball isn't rolling downhill. It's as if the system is actively pushing it uphill. The exact number they measured for the ratio of ground states to excited states was 0.88. And let me be clear, any number under 1.0 was thought to be impossible. It literally breaks with everything we've observed for decades. To put it another way, for every 88 qubits that relaxed to the ground state, 100 of them were found in the excited state. This completely new phenomenon is called hypersymmetry. Now look, a claim like this is absolutely massive. It goes against the grain of established physics. So you can't just announce it. You have to prove it's not some weird fluke or an error with your machine. And that's exactly what they did next. The first test for something like this is reproducibility. So they ran the exact same experiment on 2 totally different quantum processors. First, on an IBM Eagle chip, which is an older design with more background noise, and then on a brand new, much quieter IBM Heron processor. The thinking is, if this effect is real physics and not just a quirk of one machine, it has to show up on both. And what do you know? It did. The Eagle chip gave that 0.88 result we saw. The newer Heron chip measured 0.93. Now, yeah, the numbers are slightly different, but that's not the point. The point is that both are clearly and decisively below that critical 1.0 line. This proves it. The effect is real, and it's not tied to one specific piece of hardware.
But they didn't stop there. They went for the final nail in the coffin: statistical proof. And the confidence level they reached was 10.5 sigma. To put that in perspective, the gold standard for a major discovery in physics, like finding the Higgs boson, is 5 sigma. This result is more than twice that level of certainty. At this point, the evidence is pretty much undeniable.
So, what does this all mean? Where do we go from here? Let's wrap up by looking at what this discovery really means for the future of computing.
The takeaways here are crystal clear. First, the Y sequence genuinely suppresses errors, and we can measure it. Second, these three different modes, protection, hyperdamping, and that wild hypersymmetry, are real, reproducible physical effects. And maybe most importantly, this is a tool that works in software, it's independent of the hardware, and we now understand how to use it.
And that brings us to a really mind-bending final thought. For our entire lives, T1 decay was just a law of nature, something we had to live with. This work shows that with the right software, using the right geometry, you can actually bend that law. So it really makes you wonder, what other unbreakable laws of physics are just waiting for the right perspective to be rewritten?